So it's my great pleasure to welcome today Professor Thomas Blenkinsop from the School of Earth and Environmental Sciences in Cardiff University, who is going to be talking to us about minerals for the green economy. So he's going to be talking for about 20 minutes, and we're just looking forward to having your questions in the end of the talk. So Tom, without any further ado, I think you could start sharing your screen and start your talk, please.
Okay, well, good afternoon, everyone. Can you see the screen satisfactorily?
Yes, it's working.
Great. Okay, well, I'm going to start this talk on something of a tangent by reflecting a little bit on actually the current pandemic, which has taught us a huge number of different things. But one of those things that has become apparent to quite a few people, I think, is the fragility of our environment and the way that we interact with it. And it is to be hoped, I think, that this is going to be a powerful incentive to making changes that we all know that we need to make ultimately towards the green economy. And in particular, there are two aspects of the green economy that we know are overwhelmingly important, and that is the supply of energy and transport. And I want to focus in the next 20 minutes or so on one of the really important conditions which is necessary to make that transition, which is the supply of an adequate source of the right sort of minerals. So we're really looking in this talk at the transition from mining minerals to alternative energy and alternative transport sources. I'm going to address that topic by these 5 very simple questions. Obviously, we'll only have time to go into them fairly superficially, but nevertheless, we'll make a start on doing that. So first of all, what minerals do we need? Here is a version of the periodic table with various elements colored according to their use in devices which are going to help us make that transition to the green economy in terms of alternative energy. Now, I think many people are aware that we're going to need to use elements from parts of the periodic table that we're not really normally very familiar with, like the light rare earth elements. These elements here, which are very important constituents of the high intensity magnets that we need for turbines, for example, wind or water turbines. But what is not so well appreciated is that the traditional metals which underpin our current economy, like iron, nickel, and copper, are also going to be in huge demand in really vast quantities, as we'll see in the next slide. So while what I've called down here the special metals are of great interest and give rise to a lot of speculation about where we're going to get them from, we shouldn't lose sight of the fact that the base metals are also going to be very important. So what sort of quantities are we actually talking about? Well, again, to focus on those base metals a little bit, this extraordinary fact that a fully electric car uses 4 times as much copper as a car with an internal combustion engine gives us some sort of idea of the scale. And then these even more remarkable statistics, which have been estimated by Vidal and others, which are that if we were to replace all fossil fuels with alternative energy, solar and wind, we would be requiring per megawatt hour 15 times more concrete, 19 times more aluminium, 50 times more iron, copper, etc. And these sorts of transitions would therefore require an increase of between 5 and 18% in the annual production of these metals. That is a huge challenge to the mining industry. And certainly this quote here by Wallace Wells from his recent quite dramatic book is very appropriate about the scale of the transformation that we're going to have to make in the world's economy and in the engineering that we need to do that. So let me move on to the next question, which is how much of these resources do we actually have? And rather than answer that question directly, I'm going to show you in this table some estimates that various people have made by various different methods of the resource that might be available to us to mine for copper, one of the key minerals which in most views from economic geologists would have to be reckoned as one of the elements that we know quite a lot about, geologically speaking. Nevertheless, if you look at this table, you can see that there's almost 2 orders of magnitude variation in the estimates of what sort of copper resources are available to us in the crust to mine. And this is really the key point here. While we can make these sorts of estimates, there is a huge uncertainty in them, so that global resource estimation is in itself one of the major obstacles that we need to overcome to go forward and plan how we're going to obtain all these metals, or even if we can obtain them. I just want to briefly divert into this topic a little bit more by showing you this really fascinating version of the periodic table by Bruce Railsback, in which he shows not just the elements, but their ionic form and also the properties, chemical properties associated with the ions of the various metals. So there's here, for example, there's Fe3+, here is Fe2+. A very complicated table, and it has got a wealth of implications, but one of the simple things that Railsback did was to divide up the cations into so-called hard versus soft and see how they plotted on the periodic table. And this is relevant because when we come to estimate the amount of resources available to us, another way we could approach the problem is a strictly geochemical way, in which we look at the ultimately recoverable resource, those are the figures that we had on the earlier table, as a function of the upper crustal abundance of any particular element. Now, the advantage of looking at it this way is that we actually do know now the upper crustal abundance of elements in really quite remarkable detail. There have been progressively more refined estimates of these abundances by more sophisticated ways, and we're really quite confident that we know these numbers with a fairly high degree of accuracy. What, of course, we don't know so well are the ultimately recoverable resources, but nevertheless, there seems to be some sort of positive relationship between these two quantities, which might allow us to take the known upper crustal abundances and make some predictions about the ultimately recoverable resource. And if we do that for various elements as shown on this plot, you see there's still quite a bit of a scatter, although a good correlation. And the colors in this are, in fact, the colors of the ionic properties which were mentioned in the previous table. So they are, in fact, in this case, colored by ionization potential. And what this is basically boiling down to is that we can explain some of the scatter in this plot by looking at the chemical properties of the relevant ions. And if we combine those chemical properties with the upper crustal abundance, we might have, therefore, a really independent and perhaps more reliable way of estimating the resources available to us. At least that's a direction of research that I'm following up at the minute. So let's move on to the next question. When are we going to need these metals? Well, I think the concept of peak metals is really quite helpful here. And of course, that derives from the extraordinarily pioneering work of M. King Hubbert, who introduced us to the concept of peak oil, the point at which production starts to decrease inevitably in the life cycle of any resource. And you will probably know that Hubbert predicted remarkably accurately when peak oil would have occurred, except that he was unable to allow for the addition of unconventional resources, which shifted the peak somewhat from where he predicted it. Nevertheless, it was a remarkable piece of work, and I'm so keen on it that I want to show you a graph from his original work here, in which he's plotting billions of barrels of oil as a function of time. This is all based on estimates from the US. And his idea, which is borne out by the data, is that the cumulative discoveries would follow some sort of curve like this. There would be a time lag, which in the case of oil is 10 years between the production following the discovery, and the difference between the production and the discovered amount would give us the reserves, which would also themselves come to a peak at some particular time, which Hubbard estimated just to be after 1960. Well, I think many people are familiar with this idea, but what's perhaps not so familiar is that we can also apply these sorts of analyses to metals and minerals. And I'm showing you now a graph from the work of Northey and others, in which he's made some estimates of what is going to happen beyond 2010 by finding out what the production of copper has been from these various different parts of the world and summing it up to get the production up to 2010, and then making a forecast of what might happen in the future. And what this forecast rather alarmingly shows is that peak copper could be occurring within the next tens of years or so, which is really quite a serious concern given how much copper we are talking about that we're going to need for transitioning into the green economy. And I'm in the next slide just going to show you one other version of this sort of curve showing how copper might evolve, production of copper might evolve. And in this curve, we again see a peak of copper production a little bit later this time, but nevertheless occurring within tens of years from the present. And the point here is that these predictions are therefore converging at least sort of within a period of tens of years or so to indicate that we may have quite an important and impending copper production problem. So let's move on now to another way of looking at the same problem, namely, when do we need these elements? We can now reintroduce our periodic table and we can color up these elements by the predicted peak production time. And this is just one estimate from Svederup and others, and it really paints an equally alarming picture, namely that for some elements like gold, we may even have past peak production, gold and bismuth and tellurium. Others are going to reach peak production in 5 years or 6 to 10 years, or copper, as we've seen, in periods of perhaps 10 to 20 years. And then others, just a few of them, such as aluminium and vanadium, may have peak production well over 50 years' time. But in general, this picture painted by this slide is also giving us a lot of cause for concern and making us aware that we're going to need these, we're not necessarily going to have the availability of the sorts of quantities of these elements that we need in the very immediate future. Critical materials is another way of looking at the same problem. And in this approach, we look not just at how scarce the minerals are, but what the risk to their supply is versus their economic importance. And obviously, the higher the economic importance, the further they are to the right here, and the higher the risk, the more seriously we need to be concerned about them. And that's sometimes called the criticality of the elements concerned. And you see in this particular report from the European Union that tungsten is one of the most critical minerals at the time at which this analysis was done. So that's just another way of approaching this problem, which further emphasizes how important it is to appreciate the nature of the problem of mineral supply for the green economy. I'm now going to move a little bit away from the more geological side of the resource cycle to focus on a couple of problems concerned with the transition between the formation of the resources in the crust, which is indicated at the top part of this cartoon here, through the mining cycle, including exploration and mining, to the ultimate use of the metals in the economy. And when we look at this part of the process, we become aware of a few more potential problems. And here again, for copper, we're going to be looking at what has happened in the recent past about copper exploration. So plotted on the vertical axis here is expenditure in US $1 billion on exploration as a function of years through various parts of the world. And it is really quite an alarming curve to note that following 2012 or so, and largely stimulated, of course, by the global financial crisis, there's been a really sharp drop in exploration expenditure. And of course, the consequence for that is that we don't have the resources, or we haven't been able to locate the resources that we need to supply the minerals. That's also shown in this, this graph here, which is showing how reserves have increased in general through time as more and more resources have been discovered. But of course, at the same time, production is ramping up. And then we look at the critical value here, which is the ratio between those two quantities. And we see that from about 1980 through to the early 2000s, that curve has been on a downward trend, a very alarming trend, meaning that we're using the reserves of copper or other minerals that we discover faster than we are discovering them. Another interesting aspect of this problem, again referring to copper, is this graph here, which is showing the delay in years between the discovery of a deposit and the time in which it actually goes into production. And while in general that delay in years has been coming down, as indicated by this dotted line here, there's still a really quite significant number of years, usually, between the discovery of the product of a resource and its production. And therefore, we can't instantly expect to turn on any new discoveries that we make, which is a further compounding problem that we need to be aware of when we think about supplying minerals for the green economy. But now I'm going to turn our attention to the final question: can we get them? And in many ways, I think this is the most important question. So here is another version of the sort of resource cycle, which shows mining at the center of this cartoon. And on the left-hand side, it shows the environmental impacts of mining. Down here, it shows in the cartoon form some of the socio-economic aspects. And here is the geological aspect of resources, which feeds into the mining cycle. And of course, I've only shown a handful of the possible links between these different factors, but it's already a very complicated diagram, which is telling us something very important. It's telling us that if we are going to try to make some sort of evaluation about whether we can get the minerals we need for the green economy, it's going to be a very complicated problem, and probably a very sensitive problem, open to a lot of different influences. So let me focus a little bit on the socio-economic impacts and the environmental impacts of mining in the next slide. Okay, so first of all, what is really paradoxical about the situation that we're in is that mining itself is a huge contributor to global carbon dioxide emissions. So the very transition that we're advocating towards a green economy is in fact going to exacerbate the reason for making that transition. And that is a supreme and difficult irony to get to grips with. But even more important, I think, is the fact that mining is generally perceived by society as a very dirty activity. And there are many reasons why the so-called social license to mine has been severely challenged. And one can only think of last year of the terrible Brumadinho Dam's tailings dam failure in Brazil as one example of the reason why society is loath to think about enhancing or expanding mining activities. As I've just said, of course, the environmental impacts of mining, quite apart from their climate impacts are also huge. So global warming, but water supply, soil resources, and of course pollution are well acknowledged as consequences of mining in the past. I've mentioned already that we don't know the global resource base very well, and that's contributing quite a lot of uncertainty to our whole view of the future. And then a final problem, which I'll briefly touch on at the end of the talk, is the dynamism in the commodities market. We all know how wildly the stock market fluctuates. The same is true for the prices of metals. And for example, gold has recently been hitting heights of $2,000 per ounce, extraordinarily high numbers that we could never have really predicted even a few years ago. So just to emphasize again the adverse perceptions of environment, of the consequences of mining and the reasons for them, that Brumadinho Dam disaster in Brazil is illustrated on the left-hand side, and I really quite like to be able to contrast that with the picture on the right-hand side, which many of you will recognize as being the aftermath of the Aberfan tailings disaster just here near us in Cardiff. And there's a remarkable similarity between those two dreadful pictures. To move on to other aspects of the problem that we're addressing, we mentioned that the markets in metals are very volatile, and that's illustrated here by this sawtooth-like graph of the price of copper over the last century approximately. The reasons for some of these spikes in demand and drops in demand are known, but others certainly are not and appear almost random. And we've been beginning to approach this problem here in Cardiff by setting up some simple models which predict what might happen to the price of copper given a rate of discovery and a given rate of extraction. And what is very interesting about these models, as simple as they are, is that the outputs from the models shown down here in terms of price over 100 years show extraordinary fluctuations, even though the inputs to these models are, the inputs in ROST's models are really very simple. So what is that is teaching us is that even this system has got enough feedbacks in it to make it extremely dynamic. And probably a lot of what we're seeing in the sort of price fluctuations that we observe in the metals markets is simply an inherent aspect of the sorts of feedback between extraction prices and exploration for different resources. And of course, that makes predictions for the future very difficult. So I'm almost through now, and I wanted to end up with a bigger view of the problem here, in which we see that the whole mining and resources question is bound up with a lot of really important aspects of our global society, energy, food and water, etc. And that these are all linked together. And it's rather a useful framework to put this discussion within, that pretty well all of the Sustainable Development Goals, the SDGs, are affected in one way or another by this resource cycle. And this is a good framework, I think, to emphasize the importance of the resources to the economy and how important these general questions are that we've raised so far in the presentation. So now I'll finish off with a few quick summaries of what we've said before. What minerals are we going to need? Well, we're definitely going to need an increase in base metals, and we will need some more exotic minerals, or metals rather, from the periodic table, but these ones, it's far harder to forecast accurate demand, partly because they can be substituted one for another. How much do we need? Well, we're going to need vast increases in production of both the base metals and the less common ones. And how much have we got? Well, the interesting thing is we don't really know. So this is one aspect of research that we really need to concentrate on them in the future. When do we need them? Well, according to some estimates, we need them now or even yesterday. And most important of all, can we get them? Well, I've dwelled on the reasons why mining has to some extent lost its social license, and that in itself is perhaps the major point of this whole presentation. We need to address how to regain the social license if we are going to obtain these metals for the transition to the green economy. But I want to end up with a positive note from my point of view anyway. Geologists will always have jobs in this future. So with that, I'll end the presentation and I'd welcome questions.
Yeah, thanks a lot, Tom, for this presentation. I'm really happy, actually, you finished with a positive note. Yeah, the future looks very challenging, to say the least, but definitely there are many exciting applications of all these metals. I think, actually, the webinar of today being an excellent example. Imagine having this sort of technology without all these resources. It would be just impossible. So please, for the attendees, if you've got any question, could you use the Q&A panel, and then we could just go through these questions. I've got actually a general question for you, Tom, perhaps also a more positive note. Could you explain a little bit how this sort of research could be used by the political authorities to actually better manage the resources? Is there any interaction between the politicians and the researchers to basically make the society work better, knowing about the limitation of these resources?
Yes, that's a great question. And yes, indeed, there are huge policy implications of these sorts of questions. One easy example to illustrate that is where are these metals going to be supplied from? And if we focus in a little bit more on the supply of metals like cobalt from the very compromised operations, for example, in the central parts of Africa, we realize that there's huge ethical concerns for the supply of some minerals from certain parts of the world. And therefore, policy is a knowledge of where the resources are to be found and how much they are is going to be a key to developing good policies for dealing with the supply of these minerals in the future and ensuring the stability of their supply. And in fact, that's really the reason why the whole concept of critical minerals became so important. It was a very good way to analyze how the supply risk was going to play into that equation. So yes, there are huge policy implications, and frankly speaking, I would have thought that this would warrant a really major research effort into these sorts of problems. And there are a number of groups around the country who are involved in these sorts of questions, but perhaps not as much as is really justified.
I see. Thank you. I can't see any question in the Q&A panel. I just hope that this is not another technical issue. I don't think it would be a technical issue. You can always ask a question. You're going to remain anonymous in any case. Perhaps I could ask another question. Oh, there is one that just came through.
There is a question, yeah.
So this is a question about recycling rates, which have historically been poor because freshly extracted material has often been a cheaper option. How much could recycling get us to a steady state?
Yes, that's a really good question. I didn't really address that at all in the talk, although it's on the diagrams. It is interesting that even if you look at the most favorable possible rates of recycling, which might for some metals get up to sort of 80 or even 90%, you still find that there is a huge need for extra fresh metals to be mined. So in other words, recycling cannot solve the problem, although of course it should be done as much as it can be. So it can help, but by no means is it going to deal with the sorts of many orders of magnitude increases in production, say, of copper that we saw would be necessary.
I see. Thank you. Another question, which is an interesting one. Do estimates allow for population growth and therefore increased demand? Do we have kind of a positive feedback loop that could be somewhat paradoxical?
Yes, yes. I think all of the estimates that we looked at. Well, I don't actually think many of them don't. This is really a question more of estimating demand, which I haven't really addressed. But of course, yes, population growth is an absolutely key aspect of thinking about demand, and it's not just growth of population; it's the corresponding increase in standards of living, which of course everyone aspires to and has been happening, which is even more important actually in determining demand than the raw population growth. It's those increased standards of living which are very important.
Another question that just came through is about the extent I'm just going to read the question. To what extent is this an energy problem, in the sense that lower concentration ores take more energy to process?
Yes, Tony, that's another really good point. Yes, another of these awful sort of ironies or paradoxes that as we mine for more, we're inevitably going to be mining at lower grades, and therefore, as you say, requiring more energy to mine. And at the moment, I just can't see any answer to any other answer except that it is going to require more energy. I suppose my view is that a little bit that if we can sort of get over a threshold of alternative energy supply, then we may, in fact, be on a downward trajectory in terms of demand as well. And we may eventually set up enough alternative energy generation that we, in fact, need really to mine rather little. So if we can get everything done in a reasonable time frame, then we may have enough to survive, even bearing in mind increased population and increased standards of living. That would be the hope, at least, that this is a sort of temporary necessity for this vast increase in mining until we get these alternative energy facilities up and running.
Great, thank you. Thanks a lot, Tom. I think I'm going to ask a final question, which is more like a question that might concern us all in the UK. Do you think that because the price of the metals is going to go up, it's possible that some mines are going to open in the future that could bring in again a little bit of work prospects?
You're referring to the UK specifically?
Yeah, UK or even Wales, as a matter of fact.
Yes.
There's been some talks about gold recently.
Yes, indeed. In the last few weeks, we've seen interest in gold, which you could almost predict, given that the gold price has shot up so much. But yes, indeed. Actually, of course, there's another new mine opening up in Cornwall for lithium, and we recently had the tungsten operation down there as well, which came on stream just a few years ago and is now winding down. So I do think, actually, that it is possible to envisage a limited amount of perhaps very specialized mining going on again in the UK, but it will never be, I suspect, on a very large scale.
All right, fair enough. So thanks a lot, Tom. I think that was the last question. Thanks again very much, all of you, for attending this event today. So we're going to continue the webinar series next week, going back to the oceans and talking about plankton in the oceans. So I just want to remind you that all these events are now recorded and also displayed. They're going to be uploaded progressively on our YouTube channel. So if you cannot attend one of the forthcoming events, you can always catch up. And also, I forgot to mention in the beginning of today's event that the talk that couldn't happen last week is going still to happen somewhere mid-November, I think on the 11th of November. So thank you all for your participation, and I hope you're going to join us again next week for another very exciting talk. Bye-bye.